All right, we got a couple of questions from physics here. We're going to take a look at together here. So we had a review activity, and let's see. Concerning question 3 in the book here. Well, this isn't the book, but which was a sphere rolling down a ramp. Okay, so we have a ramp, and the surface of the ramp is really rough. That has nothing to do with the physics, actually, because in the question on page 143, they say that it doesn't actually. How do they describe it? It stays in contact with the surface the whole time. So if that's the case, then the rough surface doesn't really play into the the energy part of this problem very much, the rotational or the translational kinetic energy. Okay, so the forces that are at play here in our question is just gravity. So you have your sphere at the top. Gravity is going to try to force it down with a force of mg, mass times gravity. And it's got gravitational kinetic, gravitational potential energy, which is 1/2 mgh. No, it's just mgh, isn't it? It's just mgh. So it's going to be pulled down, for that specific height times the force of gravity. So in 3b, they talk about how, let me just get there. It says, is the mechanical energy of the ball Earth system conserved during its roll? So in the question, it says a smooth solid ball is released from rest at the top of an incline whose surface is very rough. The ball rolls down the incline without slipping. So even though the surface of this incline is really rough, because of the motion of the ball coming down and staying in contact with the surface for the whole duration, friction doesn't happen. So friction's really weird, right? Because usually with a system, like if you had a table with like a block on it and you're pulling the block across the table, that friction force is going to cause some heat. It's going to make it hard to pull the block and all that stuff. So there's definitely going to be some heat loss there. But in a rolling system, when a ball is moving along, it makes contact with the ground and is motionless for just a split second. It actually has a lot of friction there. It has like specifically rolling friction at that contact patch. So this is a pretty bumpy terrain here, but it doesn't really matter because a rolling object doesn't experience friction like you think it would. You're not dragging it, it's rolling over the surface. So you actually want good traction, you actually want high friction as it's moving along. So, when they design tires so they have good grip on the ground, so they get, the traction that you need to move the vehicle forward. So friction is removed from the idea. So then the idea is, well, gravity's making the ball move down. It's going to roll and it's going to move forward. So you have two kind of motion things happening, right? Just like in our lab, where we looked at how gravitational energy was going to be equal to kinetic energy plus like your rotational energy of that material. So it's definitely conserved, right? Because this is how much energy you start out with. It's being spread out to these two other things, but it has to be conserved. Energy has to be conserved. There's no outlet with friction and heat because it's a rolling object. So energy is in fact conserved because of that. The system is the Earth included system. So gravity affects the ball, and gravity actually affects the Earth a little bit too, which, you know, it's not going to experience that much acceleration or anything, just because of the size of the planet. So, all right, in the second part of that, it's mixing it up with a hollow sphere. Okay, so in the first one, this is going to be like a solid sphere all the way through. But then what if we replace it with a sphere that had all of its mass on the outside edge? Now, the solid sphere has the mass spread out evenly throughout the whole sphere. So it's got the same density of mass through the whole cross-sectional area of that sphere. But if you slice it in half, the hollow sphere, it would be a ring. It'd just have a single ring of mass. Center of mass is the same though. The center mass is still going to be located in the middle of a sphere, just like it would be for any sphere, as long as there wasn't like an unevenly distributed like chunk of mass somewhere that was lead or something heavier. But they do have the same center of mass. But it's like the merry-go-round, where if you have a merry-go-round and all the people sit in the center, that's going to be easier to rotate than if you have a merry-go-round where everybody sits on the outside edge. And the same is true for the ball. They have the same center of mass in the center of the sphere, but this one is way easier to rotate compared to this one where everybody's sitting on the outside edge. It's going to be way harder to rotate and get it moving. Same exact thing for rolling down the ramp. This one, because the mass is spread out evenly across the rolling object, it's going to roll down the ramp much easier than the sphere with the mass located around the outside edge. So because they're rolling down the same ramp, but they have different physical qualities about them, they will roll differently. You'll find that this one will roll maybe not much faster, but will roll faster. And this hollow one will roll slower. And that's because of I. Okay, the inertia, the rolling inertia of those is different. So rolling this one down the ramp, the inertia is smaller, your kinetic energy gets to be larger, right? If it was, the mass was all on the outside, it's harder for it to spin, the I is larger, kinetic energy has to be less, the velocity is going to be less, okay? So that's how the problem works, because if you remember, kinetic energy is equal to 1/2 mv, 1/2 mv. So the velocity is in that equation on purpose, right? So the since there's only so much energy is conserved, you only have the gravitational energy, it has to be split between kinetic and rotational. So if your rotational is bigger, your kinetic has to be smaller. If your rotational energy is, less, then your kinetic energy gets to be bigger. So they interplay together, and that's the general idea behind that. So if something's harder to roll, it's going to be slower. If something rolls easier, it's going to move faster, and it's based on the inertia of the rotating or rolling objects.